Science is one of the most important accomplishments of humanity, and its results permeate all aspects of our lives. For this reason, it's really important that we ask what science is, how it's practiced, and what its goals are, and we should question what the implicit assumptions are that are taken for granted in scientific practice. This is the job for philosophy of science, which has a long and distinguished tradition here at the LSE.
I'm a philosopher of physics. Philosophy of physics explores the foundational questions about the nature and interpretation of physical reality, mainly focusing on concepts like space, time, probability, causality, and the nature of physical laws. Philosophers of physics like myself try and clarify what these theories tell us about the universe and our place in it, so bridging the gap between physics and metaphysics. This spans the entirety of modern physics, from thermodynamics and statistical mechanics all the way to relativity and quantum physics. And it's quantum physics that I specifically focus on. A central issue in this area is the measurement problem. And this problem arises because there's a disconnect between the way the physics describes the world and what we observe. Specifically, quantum systems can be mathematically represented by superpositions, where seemingly this system is in multiple states at the same time. However, when we measure them, we observe the system only to be in a single state. This jump from many to one is what leads us to some kind of conceptual gap, as it's unexplained in the very physics. Now, the strangeness of this problem has led to arguments that the world is somehow observer-dependent, such that maybe it doesn't even exist if we're not looking at it. However, there are many, such as myself, who disagree and want to salvage an objective reality, and so we have to look to alternative possibilities. One such solution I look at is the many worlds interpretation, which predicts that every outcome of a quantum event takes place, but it occurs in a different parallel universe.
I work in the philosophy of the social sciences. This is a field where we examine how researchers study social issues like poverty, inequality, discrimination, well-being, quality of life, among many others. The main questions that are addressed are what makes a social science a reliable exercise? What are the most appropriate methods for studying complex social problems? And what might be the implications of social research on society and policymaking? In my research, I focus on how social scientists study concepts that have a strong moral dimension, like poverty and inequality. When working with these concepts, moral values inevitably come into play. For example, measuring inequality is never a purely technical exercise because it requires making judgments about how to weight the resources of different individuals and which aspects of the resource distribution matters the most for the purpose of your measurement. As a result, any way of measuring inequality must rely on a certain notion of fairness. This raises important questions. Is there a value-free way of measuring these quantities? And if not, whose values should they reflect? In my work, I focus on how economists might handle these tensions and when research outcomes can be used as authoritative sources for decision-making processes.
My research concerns both big-picture questions about the nature of mathematics and more particular questions about specific mathematical results. Considered very broadly, mathematics is quite a weird subject. Basic mathematical knowledge is absolutely essential for everyday life, and advanced mathematical knowledge is essential for serious research in the sciences. But you seem to be able to gain this useful knowledge with real-world implications just by thinking hard enough. There's no need for any experiments or observations. Even more strangely, mathematical knowledge appears to be certain. Once you've proved a mathematical proposition, there's no chance of it being falsified by future experiments, as in the natural sciences. So what's the relationship between mathematics and the sciences? Zooming in a little more specifically, There are many interesting individual results within mathematics, and I work particularly on Gödel's incompleteness theorems. These show that no correct computational system can be used to prove all mathematical truths. Since these were discovered in 1931, philosophers and scientists have ascribed a huge number of profound implications to the incompleteness theorems. For example, Nobel Prize-winning physicist Sir Roger Penrose has argued that the incompleteness theorems mean that it's mathematically impossible to create a true AI. And in my research, I've argued that the incompleteness theorems mean that there are mathematical truths that it's absolutely impossible to prove, and that implies that several classic philosophies of mathematics must be wrong. These are fascinating claims, but how is it that an ordinary mathematical theorem can have such profound implications in philosophy?
Logic is a fascinating area of study. It is the area that I fell in love with immediately when I first encountered it in college. One fundamental concept in logic is the concept of validity of arguments, whether it is impossible to go from true premises to false conclusions. To rigorously capture this idea, we need to construct formal mathematical structures in which sentences of a logical language can be interpreted as true or false. These structures are sometimes called the semantic models of a logical language. My own research in logic studies the semantics or the models. In mainstream view, or what is called classical semantics, every sentence in a logical language is either true or false in a model. There's no status in between. Non-classical semantics challenges this assumption by allowing more truth values, in particular those in addition to outright truth and outright falsity. But why the need for more truth values? Well, it's because there are very important statements in areas we care about, including, most interestingly, paradoxical sentences that seem impossible to be assigned a classical truth value. Other kinds of examples that call for more truth values, including statements in mathematics, for example, the continuum hypothesis in set theory; in physics, for example, whether Schrödinger's cat is alive; in ethics, for example, statements about what is morally good; in social philosophy, for example, statements about membership, belonging to a gender or racial group, and many more.
Models are of central importance in science. Now, models raise many interesting philosophical questions. One that I find particularly interesting is the problem of scientific representation. How do models manage to represent something beyond themselves? And crucially, how do they manage to do this in a way that allows us to learn something from the models that is valid beyond the models themselves? Because this is a really crucial aspect of models. We're not interested in models by themselves normally. We're interested in learning from models something about the real world. And the question of scientific representation is, how can we do that? And that's one of the problems that I investigate in my research. But models are not only interesting from a theoretical perspective, they're also important from a purely practical point of view. A practical problem that interests me very much at the moment is how we use models to understand hurricanes. Now, unfortunately, it turns out that constructing hurricane models is really difficult, and there is actually no agreement in the scientific community on how exactly to do this. The result of this is that there are many different hurricane models and they don't actually agree with each other. But how are we supposed to make decisions with models when the models don't agree with each other? So how are we navigating this territory? And that's the really difficult problem of model uncertainty. The problem of model uncertainty is where philosophy of science and decision theory come together.